Hi viewers, welcome to my channel. This is Dr. Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College, Autonomous, Hyderabad. In the today's lecture, now I am going to discuss the topic, the modes of vibrations of the transverse waves in the structure system. In the first lecture, we derived the expression for the velocity of transverse wave in the structure string. What is that? The transverse wave, when the wave is propagating through the structure string, the velocity of the transverse wave is given by dou square y by dou t square is equals to v square into dou square y by dou x square, where v is the velocity of the transverse wave, v equal to square root of t by mu. In this expression, T stands for tension applied in the spring, mu is the linear density. Okay. Now the general solution of this second order differential wave equation is given by y is equal to a1 sine of omega t minus kx plus a2 sine of omega t plus kx plus b1 cos of omega t minus kx plus b2 cos of omega t plus kx. This is equation 2. Say this is the equation 1. Okay. Here a1, a2, b1, b2 are constants. Now, so what we consider here? We have considered a string of length L, which is structured between two fixed ends. The first end is at x is equal to 0. The second end position, we can write x is equal to L because the length of the string is L. The two ends are fixed, right? Here we have applied the tension capital T, and the linear density of the string is mu. Mu is nothing but the mass per unit length, linear mass density, right? Okay. Right. So now, so from this, we can write, first let us apply the first boundary condition. What is the first boundary condition? There we have the two boundary conditions. At x is equal to 0, the displacement of the particle y is equal to 0. Second boundary condition, at x is equal to L, y is equals to 0. Because both ends are fixed, there the particles of the string cannot vibrate freely. Therefore, the displacement of the vibrating particle at that positions must be equals to 0. So first end at x is equal to 0, displacement y equal to 0. Substituting this in equation 2, what we get? So what is the equation 2? Y is equal to a1 sine of omega t minus kx plus a2 sine of omega t plus kx plus b1 cos of omega t minus kx plus b2 cos of omega t plus kx. In this, so let us apply the first boundary condition. 0 is equals to a1 sine omega t plus a2 sine omega t plus b1 cos omega t plus b2 cos of omega t. So that implies in the first two terms, we can take sine omega t common. A1 plus A2 into sine omega t. In the last two terms, we can take cos omega t common. Then B1 plus B2 cos of omega t. So here, since sine omega t and cos omega t not equals to 0, therefore A1 plus A2 must be equals to 0. From that, we can write A2 equal to minus A1. Similarly, B1 plus B2 should be equals to 0, implies B2 is equal to minus B1. Okay, so let us substitute these values. These values in the equation 2, then we get y is equal to A1 sine of omega t minus kx plus A2 sine omega t plus kx. Instead of A2, you substitute A1. Then minus A1 sine of omega t plus kx plus B1 cos of omega t minus kx. B2 equal to minus B1, substituting that, minus B1 cos of omega t plus kx. This is equation 3. Okay, now, so from that, let us simplify that. What is that? What we get? Right. Now, the next, substituting that, we can write next y is equals to, wait, y is equals to a1 sine of omega t minus kx, next minus a1 sine of omega t plus kx plus b1 cos of omega t minus kx plus b2 cos of omega t plus kx. సో దీన్ని మనం సింప్లిఫై చేస్తే a1, the first two terms a1 common, here sin omega t minus kx, sin of a minus b, in this sin of omega t plus kx, sin of a plus b, expanding that, sin omega t cos kx plus cos omega t sin kx minus sin omega t cos kx minus cos omega t sin kx plus the last two terms b1 taking common, it is cos of a minus b, this is cos of a plus b, expanding that, cos of cos omega t cos kx plus sin omega t sin kx plus this is b2 equal to minus b1, here this is the minus b1, okay, minus cos omega t cos kx, there we get minus, minus into minus, that gets plus sin omega t sin kx. Okay, so here sin omega t cos kx minus sin omega t cos kx cancel, cos omega t cos kx minus cos omega t cos kx cancel, then y is equal to a1 Cos omega t sin kx, cos, two terms are there. Then we get 2 even cos omega t sin kx. Okay. The next term, here sin omega t sin kx, here sin omega t sin kx, two terms are there. So you will get 2b1 sin omega t sin kx. In this, we can take sin kx common. 2a1 cos omega t plus 2b1 sin omega t into sin kx. This is equation 4. This equation represents the resultant displacement of the particle while the transverse wave is propagating through the stretcher string. In this, let us apply the second boundary condition. What is the second boundary condition? That is, at the second end of the string, at x is equal to 0, since it is also fixed and displacement y equals to 0. Substituting that, 0 is equal to 2a1 cos omega t plus 2b1 sin omega t into sin kl is equal to 0. Since cos omega t sin omega t not equals to 0, this is also not equals to 0, compulsory sin kl must be equal to 0. Sin kl equal to 0 ఎప్పుడు అవుతుంది అంటే kl should be equal to n pi. So from this we can write kl equal to n pi, where n equal to 0, 1, 2, 3 and so on. From this, k is equal to n pi by n, where k is the propagation constant. Since it is the nth mode of vibration, we can write it as kn equal to n pi by n. Okay, n pi by n. This is equation 5. But our intention is we have to derive the expression for the frequency of the stretcher string. Now, angular frequency omega is equal to 2 pi nu. According to that, for nth mode of vibration, omega n equal to 2 pi nu. Pi nu n. Okay, 2 pi nu n. That is equals to omega equal to 2 pi nu n. Right. So now, but omega is equal to velocity of the wave into propagation constant. Since velocity of the wave is equal to omega by k, from that we are writing 2 pi nu n is equals to kn. What we get, kn is equal to n pi by l. We substitute that into velocity of the wave. Pi cancel. 2 nu n is equals to n v by l. Okay, nu n is equal to n v by 2l. That equals to n by 2l. But v, velocity of the transverse wave in the string, that is we have root of t by mu. So finally, మనకేం వచ్చింది, nu n is equal to n by 2l square root of capital T by mu. This is the frequency of the stretched string when it is vibrating in the nth mode of vibration. So nu n is equal to n by 2l root of T by mu. In this, you know, T tension of the string, mu linear mass density, L length of the string. N represents the number of mode of vibration or number of loops, we can say that. Okay. Now, by then extend this thing in that formula. Entity nu n is equal to n by 2l square root of capital T by mu. If n is equals to 1, then we can write nu 1 is equal to 1 by 2L square root of capital T by nu. This is called fundamental frequency. Fundamental frequency. That means when the string is vibrating with one loop, when the string is vibrating with one loop, then the frequency is called fundamental frequency. Next, if n is equal to 2, if the string is vibrating with the two loops, then the corresponding frequency we can write 2 by 2L square root of T by loop. This is called first overtone, or second harmonic. Second harmonic. This is 2 times to the fundamental frequency. That equals to 2u1. Next, if the string is vibrating with 3 segments, 3 loops, if n equal to 3, then frequency mu3 equal to 3 by 2L square root of T by u. That equal to 3. This frequency is called second overtone. Second overtone or third harmonic. Third harmonic, because it is 3 times to the fundamental frequency. This is also known as third harmonic. Similarly, 4 nu1, 5 nu1, 6 nu1, and so on are fourth harmonic, fifth harmonic, sixth harmonic, and so on. So from this, it is very clear that the first overtone is second harmonic, second overtone is the third harmonic, third overtone is fourth harmonic, fourth overtone equal to fifth harmonic, and so on. Overtone. From the generally nth overtone is equals to n plus 1 harmonic and match. N plus 1 harmonic. Okay. Or nth harmonic is equals to n minus 1th overtone. N minus 1th overtone. Clear? Now, so from this, first let us take the fundamental frequency of the structure string, that is 1 by 2L square root of capital T by mu. In this, and when the string is vibrating with one loop or fundamental mode of vibration, if T, tension in the string, and the linear mass density constant, then the fundamental frequency depends on length as mu inversely proportional to length. From this, you can write nu1 by nu2 equal to L2 by L1. This is called law of length. This is known as law of length. Okay. Next, number 2. If length of the string and linear mass density are constant, then fundamental frequency depends on tension only, that related as nu directly proportional to root T, implies nu1 by nu2 is equal to square root of T1 by T2. This is called law of tension. Number 3, if length of the string and the tension applied in the string are constant, then fundamental frequency depends on its only linear mass density, that mu inversely proportional to square root of mu. From this, we can generalize the equation nu1 by nu2 is equal to square root of u2 by u1. This is called law of linear density. These 3 laws, law of length, law of tension, law of linear mass density, these 3 laws are called the laws of transverse vibrations in the string.